Okay, guys, today let's talk about one of the most important concepts in organic chemistry, resonance. It isn't overly difficult, but most professors do a poor job in explaining how it works or why it's so important. So remember, in this course, we crave stability. That means zero charges across a molecule. Any atom that has a formal charge other than zero is what we call unstable or reactive. The analogy I like to use most commonly is like a game of hot potato. If you can reach into an oven and try to grab a baked potato after it's been in there for an hour at 400 degrees and try to hold it for any length of time, you're gonna burn the shit out of your hand. Think of that potato as a charge, okay? But if you quickly grab that potato and toss it to a buddy, and then he tosses it to another buddy, and then he passes it to another buddy, and so on, that hot potato is gonna be spread out over several guys juggling it, and as a result, no single person is going to experience that full burn, at least for more than like a split second. So a charge, aka potato in this example, when spread out over several atoms, aka people, is going to be more stable than as if that charge is isolated on top of a single atom. So let's try a couple of examples. So all I have here on this page, I'm showing you this acid here, that's ethanol, and B with a lone pair represents a base. So if this base were to deprotonate the most acidic proton here, you would end up with this conjugate base of our original starting acid. Now, sp3 atoms cannot engage in resonance, and that's what we have here with carbon-2. So as a result, if we wanted to take one of these lone pairs, or specifically this -1 charge, and maybe spread it out over, the whole molecule, we wouldn't be able to do that because if we tried to form a double bond between carbon-2 and oxygen right here, we would be violating carbon-2's octet rule, and we can't do that, all right? In this next example here, we've got just our basic carboxylic acid, and our base comes and deprotonates it, giving us this conjugate base. Now, a carbonyl, so specifically carbon-2 and the oxygen that's bound to it in this case, they are both sp2, and sp2 atoms can engage in resonance. So I can take this lone pair here and take that lone pair, and it then becomes a double bond. So this double bond you see here, it was that third lone pair in this picture, okay? Now, for a split second, the formation of that double bond would indeed violate carbon-2's octet rule, but carbonyls have a unique ability to engage in resonance, so this double bond can basically just go chill on top of this oxygen atom in the form of a third lone pair, and no one's getting their feelings hurt as far as octet rules being broken. Excuse me. Okay, so you're going to see a lot of resonance involving carbocations. And so in this first example, this charge, and so the charges, whether they're +1, like a carbocation, or -1, so like a lone pair, specifically an allylic lone pair, they have to be in the allylic position. So that means 1 over from a double bond. So because this charge is too far away from this double bond, there's no way we can engage in resonance here and maybe better stabilize that +1 charge by moving it around the molecule. We can't take this pi bond and do this because that's an sp3 atom and we'd be violating its octet rule. So this is what we would call like an isolated charge, okay? No resonance happening here. But same molecule, but if we move this charge here into the allylic position, well, so now I can take the lone pairs that make up this pi bond, flip them over to where they exist between carbons 2 and 3. Now notice carbon-2, its octet is full now. It has 4 bonds coming out of it. But when the pi bond did that, well, now carbon-4 is missing that 4th bond that it originally had. So this is where the carbocation is now located. So because we're able to spread that charge out over several atoms, something like this would be more stable than this example where we had an isolated charge. So the goal is to always try to, if we come up with a charge, if we're able to balance it or spread it out over multiple atoms, it's gonna make that molecule more stable. This is just another example. I try to color code as best I can. It helps me to learn being a highly functioning ADHD student. So we take these 2 lone pairs, we take this pi bond, the lone pair that makes up, 2 electrons that make up your pi bond, right? And we flip them over like this. And so now they exist between carbons 2 and 3. I don't know why I labeled those 2, 3, 4. Anyway, but notice where the carbocation was here, it's now located here because carbon-4 is now missing that fourth bond it initially had. Now, resonance is not just limited to carbocations. It can also be applied to lone pairs. So in this example, it's going to be very similar to what we saw here. I can't take this lone pair and form a double bond between carbons 1 and 2 because carbon 2 is sp3. It has a full octet. It cannot take on a fifth bond. But remember, when we see charges in the allylic position, so one atom or one position over from a double bond is what we call the allylic position. Now I can take this lone pair and make a double bond between carbons 2 and 3. Well, for a split second, that's going to be too many bonds coming out of carbon 3. So the pi bond, specifically the 2 electrons which make it up, is then going to kind of just rest on top of carbon 4 as another lone pair. So here we've taken a -1 formal charge, spread it out over several atoms, which would make this molecule more stable than, say, this one where I had an isolated lone pair. Be a good chance to kind of segue into this localized versus delocalized concept of lone pairs. A localized lone pair is one we saw here. You'll see them on nitrogen, oxygen, sulfur most commonly. They're frozen in place. They cannot engage in resonance. A delocalized lone pair, just about always going to be in a allylic position. They can engage in resonance, okay, so they can move around. Just another example here, I've got this ketone with a lone pair over here on carbon 3. And so to the untrained eye, this might look like it's sp3. It's not, because this counts as a double bond, so that's going to be your allylic position, and an allylic lone pair can always engage in resonance. And no one's octet rule is violated here. I've got 2 electrons here, two here, 2 here. So carbon 3 has 8 total electrons. But I can take this lone pair and I can form a double bond between carbons 2 and 3 here. It's going to resonate this double bond on this carbonyl up here to be a third lone pair. And that's all there is to it. If you found this video helpful, but you need more in-depth explanation and see a lot more practice problems involving resonance worked out, you can find the full-length version over at orgogoat.com. Please like, comment, and subscribe to help our videos find more students like you, and tell a friend. And if you're interested in private tutoring, or if you want a concept explained that you don't see in our YouTube page, shoot me an email at orgogoat@yahoo.com.